Hello everyone, welcome back. Today's video is on the environmental mass balance. The learning outcomes of today's video is to define a control volume, and then finally we're going to analyze the fluxes in and out of a control volume. So the mass balance or the environmental mass balance is a very deceptively simple principle that mass is conserved in a closed system. So a closed system is isolated. There's no physical inputs or outputs. So that mass inside that system remains constant. Um, and so for the Earth, if we treat the Earth as a closed or isolated system with matter, there's not like a ton of meteoric like inputs of mass. So the matter on Earth is pretty constant. Atoms are not destroyed during chemical reactions. And so the amount of mass that we have on Earth is pretty constant. And the amount of mass that remains within a watershed can be calculated by this equation. So the fluxes in and out of the control volume equal the change in mass of a control volume. So a control volume is our system. It's the region of interest, the one we want to look at. You can say the control volume is whatever you want it to be. You can make the control volume as large as the Earth, as large as a entire watershed, or maybe just around a small creek or a small little region that you're really interested in. Maybe your control volume is just the flow of water through one parcel of land to make sure that the chemical pollution in that area remains at a healthy level or is at least decreasing. And so this change, dm over dt, that's a derivative. So this is a change in mass of our control volume over a change in time. So the change in mass of our control volume over a change in time is equivalent to the mass inputs of that system. The dot means it's a rate, and so it's a change in mass. It's an input, it's a flow, it's a flux in minus our flux out. So we're accepting more water, we're inputting more water into the system, but at the same rate, the cup is overflowing and there is an output of water outside of our control volume, and that's something we need to keep account of as well. So our control volume is our region of interest, and all of our inputs and outputs are defined relative to that control volume. You're only interested in an input or output of the control volume. You're not interested in changes within the system. So if I have a really large, complex system, it's a whole continent, let's say. I'm not interested in the exchange of mass within that continent. I'm only interested when mass leaves the continent or enters the continent. So your control volume helps simplify these really complicated systems and turn them into something that you can just look at the inputs and outputs of that system, because that's directly related to the change in mass of that system. And so I touched on this a little bit already, but a watershed is a form of a mass balance. The water falling on that watershed is an input of mass into the system. A mass output of the watershed could be the river flowing out of the watershed and into another region or into the ocean. You can have evaporation of water out of your watershed. You can have transpiration of water. That's the evaporation of water through the stomata of plant leaves. You can accumulate mass within your system or deplete mass within your system. And that can entail filling up a reservoir, drying a reservoir, filling an aquifer, increasing the amount of biomass in a region. If you're growing a lot of trees, if your environment is growing a lot of trees, there's going to be a lot more water in those trees than there were if it was maybe a desert before. And so if we define our control volume to be a watershed, we're only interested in these inputs and outputs of the watershed. I don't care that the water is moved from the top of the mountain to the very bottom of the mountain. And this is by no means an exhaustive list. If you can think of any more fluxes or reservoirs, I encourage you to do so. Here's another one, maybe the CO2 mass balance in the environment, the atmospheric mass balance of contaminants. Mass inputs into the environment can be industrial emissions, volcanoes, cellular respiration. The mass output of the atmosphere could be carbon sequestration into the ocean or the biomass. So once that carbon has exited the atmosphere, it's no longer in our control volume, so it's not of interest. So if it's in the ocean, it's no longer in the atmosphere, and so that is an output of CO2 from the atmosphere into the ocean. And then, of course, as you know, you can accumulate CO2 in the atmosphere as we have been doing for the last 200 years. And again, can you think of any more fluxes or reservoirs that I missed for this? There's probably not any more reservoirs in terms of the atmosphere, since it is one sort of like homogeneous system of gas. But maybe there are regions that have more CO2 than others. And so this is really powerful. So it may seem simple to be like, oh, if I put something into my system and something exits my system, I can calculate the change of my system. Well, if you decrease the size of this system and increase the number of your control volumes, you can start getting these really fine, granular, complex modeled systems where you're plotting the discharge of one control volume into another control volume adjacent to it, and more and more and more. And so that's when you get into environmental modeling, where you have a computer run all of these simulations for days and days and days, thousands of computing hours, but it allows us to take a look and predict the behavior of an environment.